A probability vector is a row matrix that shows the distribution of the total population among its states. Since they are probabilities, each entry is between 0 and 1, and the sum of all entries is 1. The initial distribution is the first probability vector. So example 6 says the probability vectors below represent the percentage of the U.S. population that subscribes to a paid video service such as Netflix, Hulu, etc. in the years 2017 through 2020. The number on the left represents subscribers, and the number on the right represents non-subscribers. Give the initial distribution. Well, the initial distribution is just the first distribution. A lot of the times that's marked as x0, but x0 is 0.469 and 0.531, meaning 46.9% of the population subscribe to Netflix and Hulu and that sort of thing. Okay? That's what that means. And 53.1% did not. Do we understand that? So this is not the same thing as a transition matrix. This is trying to describe the population and what they are. A transition matrix is trying to describe the probability that they'll do what they'll do. Okay? So it's different. Notice it's not a square. B says, what percentage of the population subscribed to a paid video service in 2019? So remember, these vectors were for 2017, 2018, 2019, and 2020. So what percentage of the population subscribed to a paid video service in 2019? That would be this number right here. Okay, now, time out. That's the probability. They asked what percentage, so I'd probably answer this question as 54.7%. Okay, very similar number, 0.547, 54.7%. Part C says, what percentage of the population did not subscribe to a paid video service in 2018? So did not subscribe, that would be this number right here. That's 48.3%. Describe the trend. Well, in general, don't think too hard. What's happening? What's increasing? The subscribers are increasing, exactly. Okay. The percentage of subscribers is increasing. Last slide. We've got a formula for finding the distribution vector for any number of transitions. This is important to make sure you get this down. Xn equals x0 times p to the nth power. That's a 0 times p to the nth power. So what that means is if I wanted to find the distribution after one transition, I would take x0 times p to the first. And if I wanted to find it after the second, I would take x0 times p to the second. And so on and so on and so on. Okay? So that's a pretty useful formula for finding the distribution. Example 7 says, recall the income class example from earlier with transition matrix that. And then it says, incomes are initially distributed 0.21, 0.68, 0.11. What that means is 21% of the population was lower class, 68% of the population was middle class, and 11% of the population was upper class. That's not talking about the probability of something happening. That's talking about the breakdown. Okay, that's talking about how many are each. Okay, what percent of the population is this and this and this. Find the distribution after 2 generations. So what they want is x2. And we can use that formula and say that's just going to be x0 times p squared. x0 times p squared. And remember, When we multiply matrices, you can't multiply them backwards and forwards. It's not necessarily the same backwards and forwards. So when you multiply matrices, make sure you multiply them in the right order. Okay? This is going to be a 1 by 3 times a 3 by 3, and that's going to be fine. If you did it backwards, that wouldn't work. Okay? If you tried to do a 3 by 3 times a 1 by 3, that's not going to work, and you're going to get an error. Okay? So make sure you do it in the right order. You have to do it in this order. Okay. So let's use our matrix calculator again, because we've already got P in there from before. So I just need to put in my x0. So we can do that. It was 0.21 and 0.68 and 0.11. And you don't necessarily have to do this, but check it out. If you click on this button right here, it'll switch them. Okay. Didn't really need to do that, but I think it kind of is easier on the eyes. So think about what we need. We need that initial times the transition squared. So that's what we have to type in there. We're going to have A times B caret 2. A times B squared. And you should notice the result is a 1 by 3, okay? The result is a 1 by 3. If you don't get a 1 by 3, you mess something up. So let's go ahead and round off to 4 decimals. And we get 0.2700, 0.5116, 0.2184. And remember what you're finding. You're finding the percent of the population. Okay, so that says 27% of the population is lower class. Find the distribution after 5 generations. After 5 generations, we're going to go x5 equals x0 p5. Easy on this calculator because we've already got everything in there. You've got a times b to the 5th power now. And, notice I had bumped it up to 9 sig fig, so I got a lot of decimal places here, right? We got a lot of decimals. Let's just round off to 4, though. Okay? So that's going to be 0.2845. .4899, 0.2257. Those numbers should add up to 1, and I can tell they don't quite. It has to do with the rounding. Since I rounded them all up, it's off slightly. We could fix that if we wanted to, round off to 5 decimals to fix it. But we're really, really close there. Okay? Any reason you're off and it doesn't add up to 1 is because of rounding here. Okay? Now remember what this means. We're talking about lower, middle, and upper. And so, check it out. You can kind of examine trends. Markov chains are good for examining trends. So look at the lower class. We started at 21% of the population. And after 5 generations, we went up to 28% of the population. So you can see the lower class population seems to be increasing. That's not really good for a population. You can see the upper class is also increasing, right? So that's good, I suppose. But you've got upper and lower both increasing, and you can see that the middle class is shrinking. Sounds a little familiar.